All right, number 36. Christian Anfinsen studied the folding and unfolding of proteins and concluded that A, disulfide bonds can be formed between cysteine, um, or B, I'm just going to go ahead and jump to the right answer. Christian Anfinsen studied unfolding RNAs and refolding it. His conclusions therefore led to the idea that primary structure provides enough information to get to the tertiary structure. B is the correct answer for number 36. Number 37. Which of the following substances is known to disrupt hydrogen bonds, and what is it commonly referred to as? B and D both have DTT. Those are, well, DTT, dithiothiotol, is an oxidizing agent, or a reducing agent, I'm sorry. So urea can disrupt hydrogen bonds, and it is a chaotropic agent. So our best answer is A for that. So that's 37 is A. 38. Which of the following is not a fate of a misfolded protein? A misfolded protein can be A, degraded, B, refolded, or assemblation. Not a word. So A and B are both true. D, aggregation. Well, we form aggregates that lead to plaques, that lead to cell death. So which is not a fate? C, the one that's not a real word. Number 38 is C. And assemblation, I did throw that word in there to kind of be a little bit of a detour or a confuser of like, oh, assembling something, but assemblation is not something. Number 39, select the statement, the true statement about hemoglobin, HB, and myoglobin. Option A, hemoglobin is a multimeric protein made up of multiple myoglobin proteins. That is something that I brought up and stressed how important it was to recognize that that is not true. B, myoglobin is a multimer protein made up of multiple hemoglobin proteins. That's the opposite of A, and therefore it's equally untrue. Hemoglobin is a tetramer, and myoglobin is a dimer. Myoglobin is a monomer, so C is out. D, hemoglobin and myoglobin exhibit a phenomenon known as positive cooperativity. Positive cooperativity is where one ligand binds, and then the protein has a greater affinity for binding those other ligands. Well, myoglobin as a monomeric protein cannot exhibit positive cooperativity. E, hemoglobin has a lower affinity for the first O2 molecule it binds than the fourth. Aha, there we go. There is our correct answer for number 39, E. Its highest affinity is for that fourth O2 molecule. The oxidation state of iron within a heme ring influences the color of blood. That is absolutely true. So if it's Fe2 plus, you've got the right colored blood, and if it's Fe3 plus, then you might have like a darker red. Number 41, which of the following combinations binds carbon monoxide with the greatest affinity? Option A is heme, B, heme plus hemoglobin, C, heme plus myoglobin, D, hemoglobin, and E, myoglobin. Okay, those last two, myoglobin, those two proteins in the absence of heme, they're going to have virtually no affinity for carbon monoxide. The studies where we talked about the toxicity of carbon monoxide was really going and looking at just heme binding to carbon monoxide. Heme has a very, very high affinity for carbon monoxide, especially in comparison to O2. Whenever you add any part of the protein, whether it's hemoglobin or myoglobin, that protein's going to kind of block the ability of that heme ring to bind Fe2 plus and to bind carbon monoxide. Okay, 42. There are two histidine residues in hemoglobin. Which is responsible for the positioning of the iron ion at the center of the heme ring as well as the O2? If those histidines were mutated, which are responsible, if those histidines were mutated to different amino acids, different amino acids, which would have the least significant impact on hemoglobin's ability to function. So we have these histidines that help coordinate and position the iron ion, help the O2 bind. If we were to mutate this, which would be the best candidates to mutate it with? Okay, so we've got histidine being mutated to something. We've got alanine, isoleucine, arginine, aspartic acid, and glutamic acid. Now, with those histidines, well, we've got something that can be positively charged or can have no charge whatsoever. So the best answer for the amino acid that is most similar to that, for question number 42, we're looking at arginine, because that's going to be either positively charged or have no charge. Glutamic acid and aspartic acid will either be negative or have no charge. If an oxygen binding curve shifts to the right, which of the following is true? A, the R state is favored. B, the T state is favored. And it's basically shuffling around myoglobin or hemoglobin. Well, when we think about hemoglobin and myoglobin, so B and D, myoglobin doesn't have a T state. Myoglobin doesn't have an R state. The R state of hemoglobin, or the T state of hemoglobin, is really what's being asked. If the curve shifts to the right, that means the P50 goes up. That means that our affinity for O2 has gone down. The T state is the less favorable, or the T state is the deoxygenated form of our protein. So a shift to the right causes the T state to be favored. Question 44, which of the following statements is true? BPG's the highest affinity is for the R state of hemoglobin. BPG causes an oxygen binding curve to shift to the left. If anything, it would cause it to shift to the right. C, when the Bohr effect is enhanced, the oxygen binding curve for hemoglobin will shift to the right. And D, when the Bohr effect is enhanced, the oxygen binding curve will shift to the left. Okay, so the first two were about BPG. The next two were about the Bohr effect. When the Bohr effect is greater, or it is enhanced, we're going to see the oxygen binding curve shift to the right. C is the correct answer for number 44. Number 45. A low P50 indicates that an oxygen binding protein has A, a high affinity for O2, B, a low affinity for O2, C, high affinity for other proteins, and D, high likelihood of binding to homotropic effectors. Well, an oxygen binding protein, this could be myoglobin, this could be hemoglobin. If it's myoglobin, it's not going to be under allosteric effect or allosteric regulation, so it's not going to have a homotropic effector. The best answer for this is a low P50 indicates a high or higher relatively affinity for O2. Question 46, something that causes the P50 for hemoglobin to increase, the P50 goes up. Is that going to favor the T state or the R state? C causes the PO2 to increase. The PO2 is something that's an environmental condition. The protein has no control over that. So that's out. D prevents hemoglobin from being subject to the T or R state. Impossible. And then A or B are our only options. So if the P50 goes up, we're seeing that curve shift to the right. So we are favoring the T state. Number 46 is A. The Bohr effect is primarily stabilized by interaction between which amino acids? Now, we've got two histidines, two alanines, a histidine and an aspartic acid, a histidine and an alanine, a histidine and an asparagine. The correct answer is a histidine and an aspartic acid. Histidine is going to be positively charged, and an aspartic acid is going to have a negative charge. So those two things are going to form a nice ionic interaction. Hemoglobin's, number 48, hemoglobin's affinity for O2 increases as it binds more and more O2. This phenomenon is best known as A, allostery, B, fluorescence, C, positive cooperativity. Question 49, heme is commonly known as A prosthetic group, a B, anthropogic group, a mesosyllibic group, or a B, beta branched amino acid? The correct answer is A, prosthetic group. Which form of hemoglobin has the greatest affinity for O2? The R or the T state, the S or the M state? The S and the M state are not real things, so we are looking for the R state. B is the correct answer for this question. All right, I hope this was helpful, and I hope you have a good day.